Bonjour, 8.6. I'm going to go quickly, and then if we need a longer video that I steal from somebody else, we'll do that. All right, we have done three main types of functions this year. We've done linear, which is y equals mx plus b. Just a quick refresher, m is the slope, b is the y-intercept. We've done exponential, which is a times b to the x power. A is like your y-intercept. It's what value we have when x is 0. And then b is your base. It's your common ratio, we call it, the number you're multiplying by every time. And then, of course, we've been dealing with quadratics. This is the standard form of the quadratic, ax squared plus bx plus c. So those are the three main types of functions we've been dealing with. And 8.6 combines them all. Yay. So let's jump into some examples. So it asks, is this linear, exponential, or quadratic? And the easiest way to know these is to plot the points on a graph. So I'm going to quickly go through these. Just looking at it, you might not be able to know, but as soon as you take them and graph them, it's pretty easy to see, oh, this first one's quadratic. If you take this and graph it, you'll find out, oh, those make a nice linear pattern. That's linear. And if you take these points and graph them, you get our exponential. So that's the easiest way, is to graph the points. Sometimes, though, if you're not graphing the right points, you'll think that a quadratic is an exponential. Linear is always pretty obvious. So one way is to plot them. And that's what you're going to do right here. So either mentally or on the graph paper in your notebooks, plot these points to determine whether this is linear, exponential, or quadratic. Good luck. All right, so boom, if you plot them, you'll see, oh, it doesn't draw the line for us. It makes a nice parabola. So those are quadratic. That is a quadratic function. Okay, now here is how you can tell without needing to graph. So linear functions have a constant difference. You are adding or subtracting the same amount every time you increase x by 1. Exponential has a common ratio, a number you're multiplying by every time. And then a quadratic has what's called a second difference that's constant, and I'll go through what a second difference is on this next slide. So this is not something that you need to take notes on, but feel free to pause this and take notes. This is also in your textbook. And I'm going to go through some examples of what these look like. So for this first one, without having to graph these points, just using a nice organized table, we can determine if this is linear, exponential, or quadratic. And the way you do that is you find the difference. And first, you want to make sure that you have a common difference in our x values, which we do in this case. And then you find how is the y changing. You'll see it's going down by 3 every time, indicating that this is linear. So it has a constant difference, a slope of -3. So this one's linear. Okay, for b here, again, you'll see that x is increasing by 1 every time. And then you'll see that y is doubling every time. So this has a common ratio. Therefore, this one is exponential. And then for c, again, it's the same common difference for x. It's going up by 1s every time. But you'll notice there's no set common difference for y. It's going down 1 and then up 1 and then up 3 and then up 5. However, if you do what's called the second difference, how is that difference changing? You'll see the second difference is constant. The second difference is going up by 2 every time. This indicates that this is a quadratic relationship. So that's what a second difference is. This is a great one to add to your notes as an example for what a quadratic looks like on a table. Go ahead and do that right now. All right, now that you've done great notes, I want you to determine if this right here is a linear, exponential, or quadratic function. Try to do this without graphing it, just from this table alone. All right, so hopefully you notice that as x increases by 1, y is multiplying by 3. Therefore, it is an exponential function. Let's double check. Yay, that's right. Okay. Now, we're going to jump into this one. So not only do you have to know first to identify whether it's linear, exponential, or quadratic, but then you also have to be able to write the rule for it. Now, we've done that for linear. In fact, we've done it for all three, but it's been a while since we've done some of these. So let's review this one. So first, we got to find, is it linear or exponential or quadratic? So you should notice here that as x goes up by 2, y is not going by the same amount, either subtracting or multiplying. But if you do the second difference is the same, indicating that this is a quadratic. So now that we know it's quadratic, we either want the vertex or we want the two zeros, the two roots. Those are usually the easiest ways to get the equation, and then we can use a form. So here we know the two roots are 4, 0 and 8, 0. Therefore, we know that two of our factors have to be x minus 4 and x minus 8. These have to be part of our equation. And then we need our leading coefficient of a. So I'll give you time to jot this down into your notes and process, make sure you understand all this. And now I'm going to move on to the next part. So now to determine what a is, you pick any other point from this table besides 4, 0 or 8, 0. So they're using 2, 12. And then you plug that in for x and y and solve it for a, like they're doing here. And then you find out that a equals 1. So now you know a is 1, and you know our roots are x minus 4 and x minus 8. So again, jot this down in your notes if you want. I'm going to move on to the next slide. Then you still have to multiply it all down. So then you multiply out 1 times x minus 4, x minus 8, and you get that is our standard form for our quadratic equation. Okay, so that was a great example. Hopefully you added that to your notes. And now you get to try one yourself. So for this one, determine whether this is linear, exponential, or quadratic, and then try to write the rule for it. Good luck. All right, hopefully you noticed that this is multiplying by a half every time. It has a common ratio of a half. Therefore, this one is exponential. And our rule is a times b to the x. Our base is the half. That's what it's multiplying by every time. And then our exponent is x. But the question is, what is a? Let me get rid of this thing here. What is a? So a, remember, is the value when x is 0. So a is 8. So there is our rule. Go ahead and make sure you understand why that, and I'll double check, make sure it's right. It is. This is a great example to write down, especially if you got it wrong just now. All right, now this next slide, you're going to freak out. Don't freak out, but you're going to freak out. There's a lot to this. All right, so we're going to use average rate of change. So slope is the rate of change for a linear function. However, we can also find the rate of change for an exponential or a quadratic, but because they're not straight lines, we have to pick 2 points and make a straight line. And then we find the rate of change between that. This is actually the kind of the bare bones of calculus. This is where calculus comes from, is this idea. All right, so again, you might freak out a little bit. You might want to jot all this stuff down into your notes. This is also in your textbook. And then you're going to see an example, and then you'll freak out less when you actually see the example. It's not as complicated as this page makes it seem. So here's our example. So we have 2 different websites, and we're going to compare the traffic between this first website and the second website. And it wants us to find a rate of change for day 10 to 20 for website A and for website B. So I'm going to go through how to find the rate of change for website A. Then you're going to do it for website B. All right, so for website A, you're going to pick for day 10 is 1,400, and for day 20 is 2,150. So it's the rise over run, just like it is for a linear equation. So you're going to do 2,150 minus 1,400. I'm going to divide it by 20 minus 10. So it's the difference in y divided by the difference in x. And you get 750 over 10, which is 75. So the rate of change for website A is 75, even though it might not be linear. All right, we're just finding a linear line through days 10 and 20. So now what you want to do is use website B's graph for day 10 and day 20 to calculate the rate of change. Good luck. All right, so hopefully you said that for day 10, it's approximately 850. You might have said 900. That's fine. For day 20, it's about 1,800. You might have said a little bit less than 1,800. So you should have a number close to 1,800 minus a number close to 850. And then divide it by 20 minus 10, which is 10. And you should have gotten about 90, 95, somewhere in there. So you can see that website B, between those 2 days, is increasing more than website A. So there we go. That is the rate of change between any 2 points, even if the graph is not linear. All right, I know that was a bit. This might not have even been as fast as I was hoping, but I will find a more detailed video if you request one. Otherwise, just let me know what questions you have during class, and I will see you then. Arr!